Yo 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 yo. All right. Make sure this is part 2 of 6.3. We're going to talk about exponential decay. Make sure you've watched part 1. I'm going to go through this one a little bit quicker because it's very similar to part 1. So you need to make sure you understand part 1 before we get into part 2. So exponential decay. Very similar to exponential growth, but now we're going the opposite direction. So it's something that reduces by an amount, by a consistent percentage rate over a period of time. Okay, and for the decay factor, just like the growth factor, instead of 1 plus the rate, it's going to be 1 minus the rate of decay. Okay, so exponential decay is when we have our graph, it's going to be going down and decreasing over a period of time, getting closer to 0. Okay, so this would be an example of exponential decay. Now, let's just get into it. So a video is labeled as a fan favorite if it receives at least 1,000 views per day. So if it gets 1,000 views per day, it's considered a fan favorite. Amelia posts a video and it gets 8,192 views on the first day. But it decreases by 25% each day after that. After how many days will it be until the video stops being a fan favorite? So this would be an example of exponential decay. So what we have here is we have our decay rate. So if I wanted to write an exponential function, I'm going to start with my initial value, which is 8,192. And then I'm going to multiply that by 1 minus the decay rate. Well, that's 0.25. And that's all to the power of x. So then I need to simplify to get 0.075, so 75% to the power of x. So this would be the exponential function that represents this situation. Now, to answer this question, what I would want to do is I would want to graph it to figure out, well, when is it going to dip below 1,000 views? Okay, and now on this graph, I can see right here it'd be on day 6. Okay, because this would be 1,000 views. So this is where, again, we would make a table and we would then start graphing our function by figuring out after 0 days we're here at 8,192. After 1 day we're at 6,100, and we would plug in our values into a calculator to figure these out, 4,600, 3,400, and then we would be down below that. Okay, so for this one the answer is 6 days, but the process and writing the function is what we're focused on right now. Okay, so decay, very similar to growth, but now we're just subtracting the rate, and then everything else is basically the same from there, but the shape of the graph has now been flipped. So the number of pica in a region is decreasing. How does the decrease in the pica population for years 1 to 5 compared to the population for years 6 to 10? So it's decreasing by 8% each year, and we start with 144. So first we need to write our function. So my function is 144 times 1 minus whatever the rate is, so that's 0.08 to the power of x. So really, my function is 144 times 0.92 raised to the power of x. Now, from here, what we need to do is we need to compare what's happening between years 1 and 5 to years 6 and 10. So really what we're looking at from years 1 to 5 is I'm trying to figure out what happens between years 1 and 5. So I need to figure out, well, what is f of 1, or when my function's 1, what happens, how many picas are we at 1 year, and then how many picas do we have at 5 years, and we're actually going to compare the rate of change there, find the average rate of change. So first of all, let's figure out f of 1 here. So let's figure out what it is after 1 year, and that's just to the first power. And what I'll find is after 1 year, there's going to be 132 pica. I'm going to do the same thing for f of 5. After 5 years, I'm going to have a total of 95 pica. So we've gone down from 132 to 95. What I want to figure out is, instead of finding the total decrease, I want to figure out what this is as an average rate of change per year. So what are we decreasing by each year in this time frame between the first 5 years? And of course it's different every single year. However, we can find an average rate of change by taking these two and finding the rate of change. So the way we do that is, again, we have our x values, we have our y values. So we can do change in y over change in x. So what I can do is I can do 95 minus 132, and that's over 5 minus 1. Because this is a point right here. When we had f of 5, we got 95. So here's my second point, and I'm subtracting my first point. I'm going to get, looks like this is going to be negative 37 over 4. Which, when I simplify, is going to give me negative 9.25. So what we just figured out is the rate of change of pica, the average rate of change, is they're going down by about 9.25 each year. Now, I know that that's not necessarily what it does every single year, but that's the average rate of change by just taking the rate of change from years 5 to 1. Okay? It's going down on average 9.25 picas each year. I want to compare this value with the same thing from years 6 to 10. So I need to figure out, well, what is the value after 6 years? What is the value after 10 years? And then, so I'm going to plug those in, and then I'm going to find the average rate of change for those. Well, for 6 years, we're approximately equal to 87 picas left. And after 10 years, we're approximately left with 63 picas if I were to plug those in. If I were to plug in 6 for x and then 10 for x. So these are 2 points. So now I can find the average rate of change of these ones. Okay, so I can do 63 minus 87 over 10 minus 6. And again, it's still a 4-year period that we're talking about here. Okay, and then I need to figure out what the subtraction is. Looks like it's going to be, negative 24. Oops, there we go. Which is going to give me negative 6 pica per year. So it's not quite decreasing as much anymore. The average rate of change is negative 6 between years 6 and 10. And it's the average rate of change is negative 9.25 between years 1 and 5. So the amount is decreasing less and less as time goes on, but it is still decreasing. Okay? So again, it's just comparing these two values. I can say between the years 6 and 10, it is only decreasing by 6 per year on average, where between the years 1 and 5, it's decreasing by 9.25. So less pica, we're losing less pica every single year, but as time goes on. But again, we're still decreasing the amount of picas that we have until they become almost extinct. If that would be like, that'd be like what happens for like an endangered species. So all I want you to do right here, though, is write 2 different exponential decay functions. So write one for this situation, write one for this situation. So pause it, write it, should be easy. So for this one, initial value 512, decrease at a rate of 50%, so that's 1 minus 0.5, which is just going to be 0.5 to the power of x. Starting at 10,000, we're decreasing, so it's 1 minus 0.12, so that's going to give me 0.88 to the power of x. I don't know what that spaz was. Okay, so last word problem, and last I think just problem in general, yeah. So we're comparing the cost of maintaining the car with the depreciating value of the car. So that's what happens. Normally when you buy a car, as soon as you buy a brand new car, as soon as you drive it off the lot, it loses some value. Okay, so the value of this car starts at $20,000, so it's a $20,000 car, decreases by 15% per year. Maintenance costs $500 the first year, and it increases by 28% each year. So we're comparing the cost of maintaining the car with the depreciating value of the car. So these are 2 different functions. This is an exponential growth function of how much money he's spending. This is an exponential decay function of how much money what about the value of the car decreasing. He's spending more each year because each year he's got to spend 28% more on maintenance just to maintain the car, and then the value is also decreasing. So 2 different functions. So first I want you to write the function for each one of these. So pause it, write the function of each one of these, and then see if you can actually graph it. So let's do that, because by comparing them on a graph, we can see the value of the car and how much money you're spending on the car, and see when it's worth it to maybe sell that car and not keep it anymore. So go ahead and write this function, graph it, and just see what you get. Okay, and then we'll compare. So for the value of the car, we're starting at $20,000. It's decreasing 15% per year. So that's 0.85 to the power of x. That's what I want to graph. For the maintenance, we're starting at $500 each year. It's increasing 28%. So I'm adding that to 1. And that's for my maintenance cost. Okay. So this, if we notice the graph, it says cost in thousands here. So this is not just $4, this is $4,000. This is $8,000, $12,000, $16,000, $20,000. So here we're starting at year 0, we're at $20,000. Okay, and then it depreciates in value by 85% or by 15% each year. So then it's going to start going down. Okay, so this is where we would want to plug in 1 here. After year 1, what's going to be the value of the car? So that's when I would do 0.85 to the first power, which is 0.85, and then I would do 0.85 times 20,000 and get $17,000. So let's see, 16, 18, $17,000 after 1 year. We're already down to, we've already lost $3,000 in the car. Okay. And then we want to keep that going. For the next one, for 2 years, we're already at $14,450. Okay, so we're pretty much right here. After 3 years, it's only $12,200. Okay, after 4 years, $10,400. 5 years, 8,800. 6 years, 7,500. 7 years, 6,400. 8 years, 5,400. We'll keep going. We'll do it one more. 9 years is 4,600. Right about here. And then that's my function for the value of the car. Now we want to figure out the function, the graph, for how much it costs to just maintain the car. So the maintenance starts off very, very low. It's only $500. Okay. But then we got to take that 500, and then now I got to start multiplying it by 1.28. So after the first year, it's going to be 640, so we're still not very much money. And then we're going to keep multiplying that by 1.28. After 2 years, we're at $800. After 3 years, 1,000. So we're still going up. I went up a little bit. My estimation, I forgot it was counted by 2, so this was, after 3 years, we're at 1,000, so we're only about halfway. So we're still staying super low, super low. Getting closer at 4 years. Closer at 5 years, almost at 2,000. And then finally at 6 years, we pass that 2,000 mark. So what I'm doing is I'm just multiplying by 1.28 each time. Keep slowly showing how much I'm paying each year in maintenance for this car. Here I'm at almost 4,000. And then at year 9 is when we pass the 4,000 mark, and we're here. So at year 9, what we just figured out is at year 9, you are spending more money on maintaining the car than what the car's value is worth. So at year 9, we're spending more money on maintaining the car, because at year 9, it's going to cost about $4,600 to maintain the car. and the car's only worth roughly just for that. I think it was like 4,100. So just a little bit more than 4,000. So this is two graphs, one of exponential growth, one of exponential decay, to compare the value and how much money we're spending. So by year 9, it's definitely not worth keeping the car. You might want to sell it because you're spending more money than you can sell it for. Okay, that's it. Decay, these are just more specific examples of how to model decay. Decay is very similar to growth. So if we got growth down, we should be able to get decay down pretty easily. Just make sure we know when to add or subtract. And that's it, guys. If you guys have any questions, let me know. But that's all I got for you. Greedy is out.